So why don't we go ahead and get started? So welcome everyone to the next meeting of the analog work group. Today, Dave Wenzloff from Michigan is to give a presentation on their work on FASoC. So I look forward to seeing that. So David, you want to go ahead and start?
Sure. Yeah. Thanks, Rob. Let me share my PowerPoint here. All right, so I pulled together a few slides. These are taken from various, prior presentations on cell-based analog circuit design that my group has been working on at Michigan for a while, as well as more recently on the FASoC program, which I think is probably what most of you are at least more familiar with if you've heard of that maybe from Betty last time. So I'll walk you through, kind of a little bit of the history, but then focus more on just what FASoC is and what we're doing with it today. And feel free to stop me if you have any questions. So high level overview, FASoC is short for fully autonomous SoC synthesis. And what it is a set of tools, really scripts that ride on top of digital synthesis and APR tools. But it's a set of tools that allow you to synthesize complete SoC designs by using correct by construction SoC design, meaning by putting the blocks together, ensuring that you have interoperability between the blocks. And we leverage IPexact for specification of the blocks and ARM Socrates for doing the floor planning and the stitching. Socrates has been modified to include floor planning for this program. Otherwise, in the beginning, we're just using that for stitching. And then we have a whole suite of analog generators, and this suite has been growing over time. So we've added, just since FASoC has started, we've added a couple to this list, but really these are the red blocks down at the bottom. And this is the focus of the talk today, is I want to get into what is cell-based analog design, or what are these cell-based analog generators, what do they do, how do they work? Since I think this group is much more focused on that, or much more interested in that right now. So that's FASoC at a high level. So we'll dig into the analog generators. And just this audience, I think all knows this, but I just want to make this point because this is really where this was born from. Was when you look at analog and digital design flows today, most of analog design is custom, meaning, or done by hand, meaning the white blocks. The green blocks here are automated, and most of the digital design flow is automated. And that's been true for a long time. So we looked at that many years ago and said, well, if we could just leverage the digital flow and the existing digital tools, then perhaps we have a shot at automating the physical design or automating the layout of an analog circuit. So really the whole goal here is to try and take what would otherwise be a full custom analog design and shoehorn it in to the cell-based digital automated design flow methodology. And if we can do that, then we can leverage today's tools or future tools that are geared towards digital design to do our layout. And most kind of the hard part, if you will, or what winds up taking most of the time for these analog designs is the layout. The layout, the extraction of parasitics, the post-layout sim, and then the redoing the layout and getting everything to pass DRC and LVS. So luckily for us, there are digital tools that can do all of that for us. So, all right, so I'll start with just an intro of what is cell-based synthesizable analog design. So I'll also sometimes call this VLSA. VLSA stands for Very Large Scale Analog. It's a play on VLSI, but VLSA is what we were calling this before FASoC. But what is VLSA? So our goal for a VLSA is to describe an analog block in Verilog. It could be a combination of structural Verilog or behavioral Verilog, where with structural Verilog, we might pluck specific cells out of a standard cell library or a library that's been augmented with a couple additional cells, auxiliary cells, I'll call them. but pluck these cells out and wire them up, you know, how you would like in order to implement an analog circuit, but to do that using Verilog, a Verilog hardware description language. So that's our goal, is if we can describe an analog circuit with Verilog, then we have a shot of running that through the digital tool flow. So I mentioned auxiliary cells. So really this is optional. Sometimes you can complete this design with just what's in a standard cell library. Other times it's not enough. You want to add a couple cells to it. So sometimes we add these auxiliary cells, but we add them on the standard cell grid and we integrate them in to a library that can be pulled into digital tool flow and APR, along with other standard cells. And then the third step here is you use existing digital synthesis and APR tools to then go generate the physical design. So that's the goal, high level.
Sorry.
Yeah.
Quick question. So I'm just curious about the usage of behavioral Verilog. So I know that you know, verification of analog designs is always a challenge, and I know there's been work done to come up with behavioral descriptions of analog design. In my former group that I had at Oracle, we were doing that using MATLAB and then coupling that with VCS. So is that kind of a similar thought process relative to behavioral description, or just curious?
No,
Okay.
Actually, you're talking about high level, more higher level user specs. So when I say behavioral Verilog, I mean you can type the function, you know, y equals a star b, right, and that will get implemented into a multiplier. So you can use your standard, more, you know, higher level or abstracted Verilog to code up, let's say, calibration circuits, or you know, built-in test, for example, or design for test. Circuits, other circuits that might augment the core analog block. So we combine these things together and we run them through the tool flow. So not modeling or high-level user spec description, but just low-level Verilog coding is what I'm referring to there.
Okay, thank you.
To contrast, structural Verilog means you're actually typing AND gate, put an AND gate here, you know, with the inputs A, B, and the output Z, for example, or put a D flip-flop here, or put a tri-state buffer here. That's structural Verilog. It's really annoying, but it lets you pick specific cells and wire them up exactly how you want. And then you can tell the tool to not touch it. Don't optimize, don't treat that like logic, don't optimize anything I just did, just leave it. But then I'm going to combine that with a bunch of other, let's say, digital functions, adders, multipliers, whatever, you know, in behavioral Verilog around that to complete the whole design.
Yes, thank you.
You bet. So here's an example, just getting to that. So for example, I could take N tri-state buffers and I could hook them all up in parallel like this, all the inputs connected together, all the outputs connected together, and then I individually drive the enables of those AND gates. Those tri-state buffers. And that gives me a digital control over the delay across this block. And I can do that by just taking structural Verilog and wiring up tri-state buffers from a standard, most standard cell libraries have them. Then I can call that a stage. I can take S stages and I can hook them in a loop, again with structural Verilog, and create a digitally controlled oscillator with a frequency control now on it, because I can digitally control those delays. So now I have structural Verilog that is parameterized, N buffers per stage and S stages, where I can fill in the blanks for N and S and produce an arbitrary number of stages with an arbitrary number of buffers per stage, produce the structural Verilog to describe that DCO. I can then run that through an APR flow and it'll drop down the tri-state buffers and wire them up just like I coded. You produce GDS and it looks a lot like digital GDS, you know. From an analog designer, you'd look at this and kind of squint or cringe. And that's kind of how that was my reaction in the beginning too. You know, it doesn't look like a normal analog layout, but there are ways, this is where we started. So there are ways to improve that significantly to get back to kind of high performance analog blocks. But I just wanted to give you this as an example of what I mean when I say cell-based circuit design. So any questions on that? That makes sense?
Yes, that makes sense to me. Thank you.
Yeah. Yes.
All right. Okay, so I mentioned that's where we started. So here's kind of the evolution of this. So we started literally with tri-state buffers pulled from a TSMC standard cell library. And we built PLLs with that. We built an ultra-wideband transmitter with that. We built an FM radio receiver with that. So then we moved on, said, okay, let's kind of untie our hands a little bit. And let's say we can build our own auxiliary cells and integrate those along with standard cells. So we built differential tri-state buffers, where now instead of a single-ended tri-state, it's a differential circuit, but it's tri-statable. And that gives you some power supply rejection, for example. And then we implemented a simple switch and capacitor, a MOS capacitor and a pass gate switch, 3 transistors, for example, and that gives you finer resolution of the delay per stage. So now with differential tri-state buffers and switch caps, you can now have a differential oscillator with finer resolution, finer control over the frequency or delay per stage. All right, then we started looking at modeling, because now getting back to the earlier question about behavioral modeling, we started looking at modeling because these circuits were getting more and more complex, bigger and bigger. We wanted to synthesize the analog circuit with the digital stuff around it. And then we wanted to know the performance post-PEX. After layout, we wanted to extract all RCs and then resimulate. And that was getting a bit cumbersome. So we started looking at modeling and ways to improve that design flow. That's moved into FASoC now. And then now with FASoC, we're also looking at things like scripted cell placement. So using Python, for example, to put more regular cell placement. Again, they're cells, they're standard cells, or they're on the standard cell grid. They follow the standard cell rules. So you can abut them, you can array them, and they will pass DRC, and they can sit along with other digitals or other standard cells just fine. So we started looking at things like custom cell placement with scripts, where you can, again, parameterize your scripts, but then lay out a more regular grid of the most critical cells. And that's how we continue to improve the performance of these analog blocks. I'll show you some examples of that later. All right, so I kind of think of this as a pendulum swinging. So we started on the left, which is kind of your custom layout generation, where, without automation. And we moved all the way to the right, which was like, I'm calling FASoC 1.0, which is, all right, only standard cells. You can't customize placement. You can't customize anything in the APR tool. You just have to lay it out like you would any other digital circuit, and we'll just see what we get. And that was swinging all the way to the right. And the complexity goes way down because we just adopt digital tools for that and standard cell libraries, all of which is available today. You're just writing Verilog at this point, but the performance took a hit. And so now we've swung that pendulum back to somewhere in the middle, where we're using auxiliary cells and partial placement of those cells with scripting to kind of get the best of both worlds. It's significantly lower complexity than trying to use an analog layout tool to do, analog design, more traditional analog design, but it's not, full. You're not just letting the digital tools do whatever they want with your analog circuit. So we're somewhere in the middle.
And then, David, do you, in the scripts part of this, are they scripts that are like custom, or just around configurations and constraints and setup around an existing digital flow? Do you have, like, the placement part, do you actually have a placement placer, or is it just, again, using the engines of the digital with different constraints or different?
Maddie, you want to answer that question?
Well, yeah, it's kind of a mix. So what Dave was saying earlier is we started with APR tools, so we used the placer, but then we upgraded that to use Python scripts to place like specific cells that require attention. Does that answer the question?
Yeah, so I'm interested in seeing how easy is it for someone to use this. Are these custom scripts around commercial tools, for example, versus something else? What if I don't have this tool, versus a self-contained script or a methodology?
Yeah.
Or being set up around an open source engine anyways, so it would allow other people to use it.
Yeah, so I was just going to build on what Mohammed's question. So what I've seen in the past and earlier lives, for a structured custom approach or high performance design is like a relative placement engine where a designer could effectively describe for a given grid the relative placement of different cells. Is that something what is similar to what you're doing with the Python scripts, or I can wait
Yes.
too?
Yeah, I'd say that's similar. Actually, I'll show you an example later of
Okay.
what those look like. But yeah,
Okay.
similar, to what Mehdi was saying, we would use Python for placing most critical cells. Like for example, the delay cells, the tri-state buffers and the switch caps in a digitally controlled oscillator. We would place those with Python in an array where they abut next to one another.
Right.
But then we would route that using APR tools, and we would use directives to those APR tools to, for example, not use a default width for a wire, right? Use a bit wider wire sometimes, or don't route over this area, for example, or for the cells that have not been placed by the script. We can use things like attractors to pull those together. Like you can usually tell these APR tools to like pull all the cells, put all the cells next to a pin. Is like these cells are critical, or this net is critical. So anything touching this net, put them as close as you can. And at least we've been able to do that with pins. So if you have a pin like clock out, you can tell it to pull all the cells close to clock out, or LDO out, or ADC input could be all the cells could be pulled close together. So that's modifying existing tools. And today we're using commercial tools. At Michigan, I'd say the Cadre Flow was developed in Ron Dreslinski's group, and that uses commercial tools. And we've already demonstrated this with open source. Mehdi has been doing that. I'm sorry, with Open Road. Mehdi has been doing that. He's been spearheading that. And there's definitely a path here to, build FASoC on top of Open Road for all of the blocks. And that's the path that we're on. But it kind of requires we add some of these features that we're taking advantage of in the commercial tools. We add those into open source tools.
Makes sense.
All right.
By the way, just Michael mentioned something, and I fall into the trap all the time. Commercial, there's proprietary and open source. Both can be commercial. So we're trying to set that tone.
Got it.
Like especially for a company like ours, eFabless,
Yeah.
we use all the open source tools to provide commercial, chips.
And similarly for FASoC itself, right? Like it's you don't want to make it sound like a hobbyist endeavor. It's actually a very professional and serious thing.
Yeah, just to be clear, I am personally going to be waiting for it to be based on open source tools so I can bolt it into other processes and we use it for commercial applications.
Yeah. Mehdi's working hard on that, Mohammed.
Yeah, so I know. I'm just letting you know that I can't wait because I believe honestly any of that work will not stick unless you continue to pull on it and provide commercial feedback.
Yeah, we absolutely appreciate everything you're doing to pull FASoC in, and the feedback is very valuable too. And let me be more specific. Like for example, Innovis, we use Innovis, a cadence tool. So we pay for those tools. So they're paid, commercial tools, proprietary tools, and the scripts, or I should say the commands that are used in scripts to drive those tools are also proprietary, which is why, actually, I don't think I ever mentioned this in my slides, but we have a private repo and a public repo for FASoC. The only thing the private repo does is just open up the proprietary commands that are used for these proprietary tools.
Okay. Well, and thank you. And I didn't mean to derail the conversation. I'm watching the progress, and I'm just letting you know that I come from a hardcore analog background, and I'm also a believer in
Yeah.
automation. So
Yeah.
because I know
Yeah.
if you know what you're doing, you will produce things that work and reliably and consistently.
Yes.
Yeah.
Yeah, me too. I'm a hardcore analog background. So, and have gone through the pain of design and layout of analog circuits, which is why, this is so attractive to me. This is why we're working on this.
Yep.
So, all right, so pulling us back. So here's our analog design flow, kind of from left to right, the entire design flow for any of our analog blocks. We adopt the same thing for all the blocks. You can see down here on this first bullet, the PLL, ADC, CDC, all these blocks use the same flow. Where there's some one-time setup that we do in order to port to a new process. And then there's every time you want to generate a circuit, you would run this part on the right. So the one-time setup is our aux cell generation. So for example, the layout of an auxiliary cell would be done once when you port to the process. We also do some modeling, and this varies by block, but sometimes this is ML-based modeling, sometimes it's more like a physics-based modeling, but we generate multiple designs using our scripts. We simulate those designs post-PEX. We take those simulation results and we use them to somehow create a model for each generator. Again, done once when you port. And then once you have the model and the aux cell library, you can go generate, you can put in your user specs and you can generate whatever block you want with whatever specs you want, as long as they're achievable with that design. You run that through digital synth and APR, you get GDS, you do post-PEX extraction, you simulate post-PEX, you can do whatever verification you want. Any verification you'd normally do on an analog block, you can do it on this post-PEX design. That's what we do. And then once it meets your specs, then we add it to this library. We call it our COTS library, commercial off-the-shelf library. But we add it to a library of blocks that we've now designed and verified. And now FASoC, the high level, the SOC generator, can pull from that library if it exists already, or if it doesn't, it can go call an analog generator to create the block and then pull it in after it's been created. That's basically our flow.
Hey, Dave.
Yep.
Yeah, question. So do you generate cell abstracts? By that, I mean such as a timing abstract or noise abstract or power as part of that? Or is that really still done part as a SPICE simulation effectively in the end?
SPICE simulation, although we are looking at to speed up the modeling of our timing circuits, specifically like DLLs, PLLs, things like that. Mm-hmm. We are looking at the timing information generated by a tool like Liberate when it, yeah. So we're looking at that because there are, when you lay these out, like the timing information that gets generated is pulled from all this data that comes out of these cells, and we've been comparing that with some of the SPICE level sims of some again, timing-based circuits like oscillators or delay lines, long delay lines, and they're pretty good at predicting what the performance will be. So we're looking at, how accurate that would be if we just skip the whole SPICE sim part and just use the characterization. But that's what my PLL student's working on now. So that's kind of too early yet, to say for sure how well it's going to work. But sort of out of necessity, because these things take forever to simulate as they get bigger and bigger.
Right.
Yeah.
I mean, another approach that we had looked at back in my industrial days was we had a mixed mode capability for our gate analysis tool, so that depending upon what the design was, in particular, such as the clock grid, we actually were able to dive down into the SPICE level representation and simulate it. And then annotate that dynamically back into the gate level, but that's a further out topic.
Just for the clock grid?
It was a combination of the clock grid was done at SPICE level, but then the remainder of the design was done at gate level.
Yeah.
Using, Liberty abstracts.
Yeah, interesting. Yeah, Rob, I'm going to follow up with you on that, because that's something we've been. Yeah, I'm curious if we've been looking at ways. Is there a way to basically cut some wires, generate an entire GDS, but then just cut some wires and do post-pex on just the part I snipped out and simulate that, right? So, you know, but I don't want to simulate, you know, all the digital. I just want to simulate part of it, part of my circuit. It doesn't include the digital, so to speed it up. But we've not been successful at finding a way to like find the design, first of all, and then cut it out and just simulate it. So yeah, I'm interested in that.
Okay.
If you've been able to do like the ClockNet, it's kind of the same thing. You know, it's carving out part of the design. Yeah.
And by the way, just while we're mentioning that, I don't know if people are aware or not. So we've been involved and we had worked and used some setups for mixed mode simulation, mixed simulator simulation, like iVerilog with ngSpice together, running a mixed mode design. It's not, this is just a simulation aspect. The Spice netlist can have whatever you would have, whether it's extracted or not, right?
Yeah.
But it's not selective, but it helped us a lot in getting rid of the, you know, like simulating a digital in the digital world, right?
Yeah.
And it's higher performance. And also we made some modifications to ngSpice to dump the same formats, like you can open them with the same viewer together, the digital and analog waveforms in the same viewer. And also we've done it a couple of times, and actually we have real case examples. The problem we have, which I'm trying to solve now, is that I'm trying to actually put an application note about this, because it's becoming an issue in the Google / Skywater in general. Okay. And we've done a couple of tricks, and we did it on a chip like Raven. So anyway, so it doesn't solve your problem by selecting one net, extract it, and go through it.
Yeah.
Okay? And I bet you there will be, you know, I mean, I know back 20 years ago, or at least, 20 years ago, when I was working back on Cadence and things like that, there was a, you know, selector net to be extracted, but it always decouples the caps to ground, for example, or instead of the cap to neighboring, you know. So there's some approximations there, but they were good. They were okay as long as you know that they're approximations, right?
Yeah. Good point. Thanks for the feedback. I'll probably wind up following up with both of you on those. Well, quick time check, Rob. We're at 12:29. I think you said 30 minutes. So I just want to see where we're at with time.
I think I'll let Michael's on board now. So Michael, I think we should let Dave keep going. Any thoughts from your side?
Absolutely. If we could just kind of cut out some discussions so that we can kind of have it at the end.
The discussion's the best part.
Yeah, I know. It's hard to manage it, but
I'll stop asking questions. I apologize.
No. Those are the best. That's the best part.
I'm actually against Mike on this, so we're gonna have to debate that outside.
Let's discuss about not discussing. No, okay, sorry, I didn't mean it like this. Let's discuss absolutely. It's just let's be conscious of the time so that we make sure that we kind of have time to cover other things.
Actually, my back end slides are more quick kind of examples. So really the meat, I'd say, is in the first half of the deck. And again, I sent the deck out. You guys can poke around if you want ahead of time.
The worst part is the examples are typically the most interesting, for me at least.
All right. Yeah, okay. Maybe I shouldn't have spoke then. Yeah, maybe we'll spend more time talking about that. So actually, just kind of digging in. So let me first show you an example of a differential DCO that we built with this approach that implemented, I think, a really cool feature that we've been looking for other applications of this same thing as well. But I'd say one of the cool things that you can do when you have access to kind of this methodology is like look at other ways to get. In this case, we looked at fine delay control of the oscillator or fine frequency control using pulse width modulation. So rather than driving the control signals as always on or always off for a tri-state buffer, we would pulse width modulate those control signals at the clock frequency, at the high clock frequency. So instead of you'd get let's say it's a 1 gigahertz oscillator. We would have a pulse that every clock cycle, every 1 gigahertz, every 1 nanosecond, you get a pulse, and we'd be able to modulate the width of that pulse using a cell-based circuit that produces a PWM block. And by just pulsing or controlling the width of the enables of the buffers, you get much finer control over that edge. Think of falling edge or a rising edge. You can just barely tweak that edge with a little bit stronger buffer just for a small period of time, and you shut it back off. And so you can barely tweak the edge, you can get very fine control. And this gave us actually a huge improvement in resolution, which in an all digital PLL, that means, lower noise, lower spurs everywhere. So gave us much better performance. And actually, this is the first cell-based PLL that we used in a radio. I think we used this, I think we did a 400 megahertz med radio, a binary network, W-band radio with this. But this is the first time that we used a ring oscillator that was automatically generated for a radio, meaning the phase noise performance is good enough for radio. So, all right, so that's PWM. So that's kind of an aside. If you look at individual stage, it'll have tri-state buffers, strong tri-state buffers, weak tri-state buffer, and switch caps. So there were 3 auxiliary cells that we built for this PLL. Each cell you would then lay out on the standard cell grid. Today, we are using Align to automate the layout of aux cells. We've actually been going back and forth the past 3 weeks to implement. We have 5 cells now implemented. 5 of our aux cells in FASoC are automatically laid out using the Align tool in GF12. So we're working on expanding that to the rest of the cells, but we can automate the layout of these standard cells as well.
And then this is just a question about Align. Is Align dependent on other things, or this is independent? Do you give it the rules and some guidance on the technology, and it will do it? So basically, when you move that to Skywater, will it be usable?
Yeah. Well, you'll have to. So if Sachin's on, I would turn it over to him to answer, but it doesn't look like he's on the call. So Align has a configuration, right? That is PDK specific. So you do have to, if you're going to port, just like porting any.
Yeah. So technology information and.
Yeah, you got to port the new technology information. So I think that's a given. Any tool is going to have to do that at some point.
Yep.
So when you
does it depend on a proprietary tool, another tool?
Yeah. On another tool.
Align. Does Align is a self-independent? I don't know what
Oh no, it's not dependent on. It's not. It's self-contained. Okay. It's not dependent on another tool. Yeah.
Great.
Yeah.
Thank you.
Yeah. Okay. So then once you have the cells laid out, then you can do things like build a single stage macro where for one stage, I'm going to take all these cells and I'm going to place them in a macro so that when I drop down, let's say 5 stages, each stage looks the same. It's using the same macro. So then I can drop down stage macros to assemble a full DCO connected in a loop, and then APR the whole thing. So the only custom layout at this point is just to generate those 3 aux cells. That's a one-time porting cost. After that, you can scale number of buffers per stage, caps per stage, number of stages to get a wide range of different DCOs from this, all generated and APR'd using the digital flow at that point. So here's what it looks like in GF12, and this is now using Python scripts to structure the placement of fine and coarse cells. Notice stage 0, stage 1. So a stage goes across the top. So stage is short and fat in this layout. Notice the structure of the aux cells, but then that DCO sits right here in the middle of the rest of the PLL, which is all APR'd. So the rest of the PLL is all APR'd, and then we surround it with decoupling capacitors. So that was taped out in October.
I'm just curious, Dave, do you always use a commercial router for these things, or do you also
We
have
do.
your own,
No.
structured router? Okay.
No, we do. We always use we just try and drive the router. Like if we don't want it to use minimum width wires, we tell it non-default, rules,
Right.
for example. So we just try and drive the APR tool using whatever's available command-wise from the APR tool.
Okay.
Yeah, rather than trying to build our own tool, which we didn't want to do. We just want to leverage. We're letting other people build the tools. We want to drive things on top of it.
Okay, understand.
Yeah.
David, this is Andrew.
Yeah.
Sorry to interrupt. Do you drive this all out of Cadre?
Yes.
Okay.
Yeah.
And OpenRoad, I was just asking Mehdi, it's not in Cadre at the moment.
Correct. Not today. Yes, that's correct.
But is there a timeline or a plan for that?
A timeline to get the Cadre flow, I'd have to ask Ron that question. I think right now the plan, Andrew, because we're doing OpenRoad, and I think right now the plan is to stand it up outside of Cadre, and I think that's what Mehdi has done for his takeout.
That makes sense.
When those two things converge really comes down to when Ron's going to throw some resources on that. And I don't have a good answer for that, meaning it's not in the next couple quarters.
That makes sense. No, Mehdi has shown us some screenshots that look really interesting. So I know you are working outside of Cadre then.
Yes, that's right. Yeah, we are.
Thank you.
Yeah. Another example, LDO for power regulation. The schematics shown here down on the right, very simple LDO with a PMOS switch and controller, and then some kind of comparator. We've implemented a few different versions of that comparator, all cell-based. So here, just showing what it looks like, pre-PEX simulation of max load current versus the size of the array. And then once you run it through APR and just randomize things, what happens to that max load current? First of all, it goes way down. And then second, it gets really bad. The variation gets really bad. And this is due to the unpredictable placement and routing, but that's not the end of the game. So we apply some tricks here on the left to cut down on the loss resistance using, again, non-default rules. And then we use some more structured placement of those cells to get more regular placement with the APR engine. And we can get that nice, relatively smooth curves back, and we get the load current back up to where we wanted it. So just an example of, all right, if you just give it to the tool, and let the tool do its thing, you probably won't get what you want. You might be able to use it, but it's not going to be as good a performance as you might want or need. So we drive the tools a little smarter to get that performance back. Mehdi has been working on our ADC. We've built a SAR ADC. So you can see a schematic at the top. We put a couple ADCs down in our last chip. And here you can see Mehdi has been playing around with some common centroid placement. Again, using script placement of the cells, but can do things like common centroid layout in a scripted way and make it parameterized, make it scalable. In our last GF12 tip, we also dropped down a Bluetooth transmitter. So complete radio, including GFSK modulator, Gaussian frequency shift keying. That's what Bluetooth uses to communicate. A PLL, a ring-based PLL to generate the LO signal, LDO to drive the power, and we use the switch cap PA. The switch cap PA was custom. This is the only thing that was custom laid out in this design. Everything else was run through our generators and flow. We are now looking at making a cell-based version of the switch cap PA in order to make that synthesizable as well. That's one of the new blocks that I was talking about we're adding. All right, so pulling that all back together to the top level flow chart. We've been talking about basically this bottom part here about generating analog blocks using these analog generators. We have the PDK and the cell libraries come in. We generate some aux cells. We generate some models, and then that feeds our analog generators. We populate a COTS library from those analog generators, but we've also built this datasheet scrubber that can just look at a PDF, like a conference publication or a datasheet, and can pull out some specs and put that into a library to help inform the SOC on kind of what's possible. And then our SOC gets trained. We have models for the SOC that help take user specs and then choose what to pull from these libraries in order to build that full SOC. We've built a couple of those today, one in 65, one in GF12. I intentionally drew these to scale. I shrunk this guy so they're to scale. And the thing I'll point out here is the LDOs from 65 to 12 got smaller. The PLLs from 65 to 12 got smaller. The memory got smaller, but that's probably not a surprise to everybody. But you know, how many times can you say, you know, when you port an analog block from you know, to a more advanced node, it gets smaller, right? That's pretty rare, I think. And so because we adopt this cell-based approach, we use, you know, things that mimic the standard cell library and digital cells. We actually do see some improvement in terms of scaling when we jump to more advanced nodes. So we can kind of ride that Moore's law or scaling as well, which I think is just another advantage of the approach. A couple more slides. One, I asked all the students to measure the time it took to port from 65 to 12, and this is what they reported. The cadre setup took about 2 weeks. That's our digital flow. So we had to set our digital flow up, and that took about 2 weeks. But then if you look, every generator took on average about 2 weeks. The SRAM took a little longer, but everything else took about 2 weeks. These are 8-hour days, but 7 days, 8-hour days is what I told the students to assume. So about 2 weeks of a single designer's time to port from 65 to GF12. And then once you're ported, then you can now generate these designs very quickly. I've mentioned a couple times already the effort to port to Skywater. So thanks, Mohammed, for all your help on this too, and Google. So Mehdi, who's on the call, he's been leading this effort. And so far we've ported the LDO and the temp sensor. And ideally, we port all of our blocks and our whole flow eventually over to all the open source tools and PDK. So that's our plan. That's it. I'll leave you with a couple links. I put Google and eFabulous on there just because I know that they are also looking into FASoC, so might be another good resource to go to if you're interested in more info. And Rob, I left us 15 minutes. Hopefully that's enough.
No, that's Dave.
Oh,
thank you so
enough.
much.
Yeah.
This was great. Thank you so much, and I really appreciate the details and entertaining our questions too. So yeah, I'll turn over to you, Michael.
And thanks, Rob, for the idea. Right, you came up with the idea of having presentations. I think it's a great way to get products introduced. I think this is awesome, David and Mehdi. I think the most important kind of question that's in front of us, in a sense, is how do we enable FASoC to kind of go towards commercial use and kind of use in projects that either otherwise wouldn't be possible. That's kind of one example. There's kind of certainly this space where open source suddenly enables things that people didn't think were possible because nobody's interested in those use cases. Or how do we kind of plug them into existing open source efforts where proprietary alternatives do exist, but for this or another reason, people are excited about doing things the open source way instead, because that gives them some other paybacks further down the road.
Yeah.
And how can we help? Not just, we don't just want you to kind of come and present and we all nod our heads and appreciate the great work, but more how do we kind of plug more people into the effort? We have more brains here that can potentially assist, and more people working with other open source projects. Martin, you raise your hand.
Yeah, just a question. David, thank you very much for the presentation. And I particularly appreciate that you had your students track the time for the porting of the design to multiple processes, because this is data that I love to see.
That's the best slide, yeah.
Question about, is there a place where we're going to be maintaining these talks? I mean, David and Rob, are you going to share these or post them, archive them?
Oh, Martin, you're not on the distribution list?
I am. I was just wondering if they were going to be actually archived through CHIPS Alliance.
Let me look into how to go do that, both archiving the presentation as well as the recording of this, which we are doing.
Right. Okay, excellent. Yeah, because I think that could be a really useful resource as well.
We can put the presentations up on a GitHub repo, and then Rob, when this recording's done, I can put this on our YouTube channel.
Oh, thank you so much, Brian. Appreciate it.
Sure. Yeah.
It'll be on YouTube, Dave.
It won't be the first time, sadly. Sadly. Yeah.
And not last.
Yeah. But
so did you identify anything that kind of you could think of as potential early adoption use cases outside of
Yeah, Mike, I was going to come back to your question. So you mentioned like commercial use, how do we drive that? And then how do we plug into existing open source? So on the commercial use side, the way, so I've had students do internships. I know that's not the answer you want to hear, but that's one way that we've gotten these tools stood up at other companies, if that's what you mean by commercial use. And that includes, I mentioned Cavium Networks, but also Intel and Motorola, AFRL, to name a few. I think those are the four where we've stood up. We've had interns, students go and specifically do interns to stand up the tools. So that is one way to certainly do it. And that is because when you go into a company, they're going to have their own tools, their own tool flow, right? Their own PDK if you're Intel, and we can't see that. And so you kind of have to stand things up there in their design environment. So I am certainly open. I'm not a tools guy, so I am open to ideas there on how to make these things more portable. I know there's a lot of tools people on the call. So
let me speak to that, because that's what before even the Skywater Google, we used only open source tools for commercial use. Now, what I believe is that once it's migrated to Skywater, this is going to be if put in an easy way to install and use like a package. And I know the Skywater program has a little bit to improve about making it easy. So I have a view, I want to put this on the cloud, Google Cloud, let Google pay for the cloud, and actually have people upload net lists and use it as a design on the cloud type of approach, and then get something out of it. Short of that would be like a container. I can guarantee you for sure, I'd like to use it in IP generation, depending on which IP you guys are already there. So because there's an analog vacuum, if you didn't notice, on Skywater today, right now, at least in the open source IP type of. So they're having also some of these blocks generated and published, like similar to the temperature sensor LDO, and that is actually going to be useful to show that the specs of these blocks have been generated using this, and that actually that would actually drive the attention of the analog designers. Analog designers in general, they won't believe in that. My view of that is that show their specs. People listen. And show the specs and the slide about timeline, because that's how I argued. I didn't argue. This is how I made the point to TI. You design for specs for the same specs or better or first time success, and then challenge them and say, okay, well, we're doing this and we're doing it shorter than time than the other guys. So there's something to be learned there. And then they start, everybody wants to look good, wants to be productive, not just ego. So they once they see results and in a good timeline, they say, I want to do this. So I think having published results and measured and in a good methodology and good characterization around it it will actually go a long way to pull the tool in. That's my view.
Yeah, just elsewhere we've had success is if you kind of go one level above that to the end user of that analog IP. So not
but people who don't know, historically, people who don't know analog,
correct,
are happy, are best customers for analog generators.
Like me.
Yeah. Yes.
Yeah. This is true.
I'm a spy from the digital world.
If you don't know that example, like Serenova, the company back when they would go sell it to analog, and ended up Intel was getting it because they wanted some sort of automation around certain things that they didn't want to have they need a codified knowledge for that. So just make it on SkyWater, and I guarantee you it's going to take its own path.
Yeah, I mean, SkyWater is the obvious thing because it's an end-to-end. Suddenly it becomes an end-to-end
with open source tools. And again, when we're saying, I know it's happening, so I don't want to have any subtle pressure on Mehdi or anything.
Yeah.
but it's happening. I mean, just to add to Michael's question, there's a lot of FASoC relies a lot on tools, and we are lucky to be working with Andrew and the Align team. So these are good enablers to get FASoC up and running on open source tooling.
Yeah, and I have the note several times here. One of the things about SkyWater and open source analog related activities is that they're not encapsulated in a way that are easy to be used. It doesn't matter whether it's including Align, Magical, So I want to have an effort to take all of these and make them available in at least a container of some sort, including, of course, that will include OpenRoad in a way that is used directly, rather than having to deal with the need for a software comfortable personality.
So when you say container, are you referring to Fuse SoC or Idealize?
No, and this is not on your end. I'm saying on the user end, I'm talking about Docker container.
Okay.
I don't care about any other thing. I want something that within 5 minutes, somebody's up and running, no question. So I'm not telling you to do it. I'm just saying, because I know there are so many constraints about that, but the idea is to make it easily usable so people can evaluate it and see the results. That also changes the dynamic of how fast that can move forward.
Cool.
Yeah, Mohammed, something like if there are examples of that, I think it would be good to use those as templates for how we might do it for a tool like FASoC. Like, is it true that you could stand up a digital tool flow in 5 minutes and be running?
5 minutes if you exclude the library.
Yeah, that's the thing. You always, it's like
so
5 minutes, but if you assume this other part's done, right?
Yeah, so my view is that I have, like, for example, eFabless, we have an online cloud platform that has everything, analog, digital, everything.
Yeah.
I have it in a container, but I have the PDK bolted into it or removed. And I just sanitizing it, making sure there is nothing proprietary in it, so I can potentially put that container. It's called Chiplicity, the way I call it. And it has, you can log in, you can run the container, and it opens a session for you. You can just run Spice, run digital flows, run. So I would like to add, once I get to it, or somebody would get to it, I would add that into the container, and I can show it to you. Maybe that would become just another build, another part of the build. So no, all the other guys that are involved in the tools, they will tell you just avoid containers. I'm saying, I'm sorry. There are.
Excuse me. Who would tell you avoid containers that's involved with tools?
Well, Tim Ansel, for example, and then now I know there are good reasons for using.
We're doing a lot of container work for Tim Ansel, so.
So anyway, the idea is to have a quick, for someone to say, you told me that right now. In order for me to enjoy or go try what you're talking about, there's a huge barrier. Just what you presented.
Yeah. Actually, Mohammed, so you bring up a good point. So I would say, when I think about setup, I think about all the work that you did behind the scenes to make it so that somebody can just get set up in 5 minutes. But when you're thinking setup, you're thinking someone comes to your environment, and now once they're in your environment, they can get set up. So I'll give you another example of that. When I bring on a new student, who hasn't used this before, they are in my environment, and that setup is very fast.
Yes, and that
it's
is
enabling access to a few different paths. It's cloning a repo, and it's running an instruction.
And that has its crowd, and it's useful. And then obviously the other end is useful as well. I just want to historically, you know, I don't want anybody to have any reason not to be able to tangibly see the results.
Yeah. But that's the, you know, when I think of setup, I think of, you know, taking this and setting it up in someone else's environment.
Okay.
Yeah, which means you need the libraries, you need the tools, and you need you know, you need all this stuff, right? And
well,
that's why I was saying, are there examples of that where that's been done in 5 minutes or 10 or a day even? You know?
Yeah, so I maybe, I'm sorry to open the topic or why, but it's important. So, you know, I'd like the tools that are coming out of this program, this group as well. Many things, like I saw a couple of people on Slack, they're saying, I'm trying BAG and I'm trying Align, and then so there's Magical. So I am trying to say to people, as much as you promote the tool and its capabilities for design output, it is actually key to make it easily accessible by someone without even the emotional barrier. So I'm not saying you do it again. I think we have a process that can include this. We actually have a Docker container that's like a Docker file that you can specify what you need, and then we'll just rebuild that thing anytime and add to it lines as much as you want. So as I said, I'm just in the process of making that available as an open thing so that we don't become the only people to maintain it.
Cool. Yeah, that's great.
Yep.
I like it.
Okay. We're running out of time, and we won't be able to push over 7 p.m. Andrew already had to drop. So sorry, 7 p.m. for me, obviously kind of early in the day for most of you probably. Anyhow, we have a bunch of things that we didn't manage to do today, and I think it's fine. I don't think we really need to. We can kind of continue over email. Remember, there's a mailing list. We should definitely start like exchanging emails, not just meeting. I think presentations are a great idea, so we need to line up presentation for next time. We have, by the way, the Align framework is kind of reaching out to join us as well. So hopefully we can get projects in faster than we can kind of run out of presentations to cover. Obviously, won't be able to do that, but let's at least try to keep this up for a little while. And let's continue next time with the presentation. 2 weeks, I think, is a good cadence to run fairly fast, but not too fast. I mean, everyone's busy, so I guess we'll try to find a slot 2 weeks from now. I don't know if Tuesday is acceptable actually, because we started off on a Tuesday and we exceptionally moved this to Monday this week, but I don't know if Tuesday works. Or should we send a doodle out now that we have a bunch of people? I think perhaps a doodle is in order.
Yes, that's better because you know.
Or we had this Excel sheet, right, Rob? Because
there is an Excel spreadsheet that I
okay,
have.
we can use the. Can you paste it into the meeting notes just so that everyone's aware?
Yes, I will do that.
Okay, I gotta go.
And everyone express their or send it to the group. Yeah, Rob, please send it to the group. And then
okay.
Have a good week. Have a good week, guys, and thanks, David.
All right.
Thanks, Rob.
Good to see you.
Yep. So Excel sheet it is, our own personal doodle implementation. Thanks, guys. Thanks, David, for presenting.
All right.
And
thank you, Dave.
Yeah, thanks again.
Bye-bye.
Take care, everyone. Bye-bye.
Bye.